suppose a Lie group is given. Then we choose a suitable neighborhood of the unit element, identity element, and we imagine that for group elements in this neighborhood, oh, by the way, neighborhood is a technical term. It's not just nearby. It's a term in topology. It is an open set with certain properties. So we imagine that for all the elements of the group in this neighborhood, we are able to assign real coordinates or parameters. Now it's a matter of general convention. The number of real independent essential coordinates or parameters is called the order of the group, and in the theory of compact Lie groups, usually the symbol R is used for this order rather than N, which is what we use for number of variables in any argument. So I will start using this letter R for this purpose. So for example, for SU2 or SO3, R is 3. So we say that is the dimension of the group or the order of the group. These words mean, of course, real, you know what it means. Independent means that you have certain number of coordinates or variables. They can be independently varied. You can keep all of them fixed but vary only one, and so on. Essential means that you are unable to describe all the elements of the group in that neighborhood with a smaller number of independent parameters. So this is as much as you need and exactly what you need. So I will draw a picture for this purpose. Maybe I will draw it in the right hand side here. This is a depiction of small r dimensional Euclidean space. Always we write Rn, but I am now using little r. This, as I said, a matter of convention. And let us suppose this region of Euclidean r-dimensional space is what is used to describe in a one-to-one manner continuously elements of the group in the neighborhood N of the identity. So I use the same symbol N, whether I am talking of a region in the group or the corresponding region in the parameter space. So, for example, you will say, I keep walking back and forth, I think this video will get a headache. You take an element A in the group. In that picture in Euclidean space, it will be represented by a point with coordinates alpha, superscript j going from 1 to r. So sometimes in many formulae we have to use the components alpha 1, alpha 2, etc. Sometimes we view them collectively. So let us suppose this is the point in Euclidean in the parameter description, parameter space, denoting an element A of the abstract group. Then you consider some element B. It will have a set of coordinates. And this notation which I am introducing now, it is very carefully planned notation. So I will be going a bit slow. So let's suppose that this point in Euclidean space has coordinates beta and represents the group element small b. Now, for all the general discussion, we will assume we are considering elements in this neighborhood and therefore in the parameter space in that big oval. All operations will be limited to that region. So I don't even have to say it, but let me write both A and B are imagined to be within the chosen neighborhood. Now we make a convention. Just for convenience, always the unit or the identity element in G, which is also in the neighborhood N, will be assigned the coordinates or parameter values 0. So in this picture, the origin corresponding to the r-dimensional vector 0 represents the group element identity. So what you have to imagine, I did not draw one more picture, namely the group itself. As the element little a moves around over this neighborhood of the identity in the group, the parameters describing A run around this region of r-dimensional Euclidean space. And as I said, I have denoted this region in parameter space by the same symbol n. Now you can see that it is to be therefore understood that there is a one-to-one correspondence between group elements in this region of the group and points in parameter space in that region. Okay, that is to be understood. Moreover, it is to be understood that this assignment is continuous. Now, what does it mean? I am not going into great detail for this definition of this term. All you want to say is that a Lie group is a particular case of a topological group. Therefore, the concept of continuity makes sense independent of whether you use coordinates to describe it or not. A topological space has built into it a notion of continuity. Ordinary Euclidean r-dimensional space has an ordinary notion of continuity with neighborhoods, open spheres and so on. So it is meaningful and it is important to agree that this assignment of parameters for group elements is a continuous assignment. It is one-to-one continuous. It is to a limited region of the group, limited portion of Euclidean space. Okay. I had equation number 2. Now, you can see, going back to the case of SO3 or SU2, we used several coordinate systems. Let me go from the bad example, the Euler angle, which is so useful for all practical quantum mechanical calculation. Is that a coordinate system agreeing with the conventions I have described up to now? No. Why? Occasionally, not all the time. There are some edge problems. Moreover, the identity is not unambiguously assigned 0 values. Remember, in the Euler angle description, if this psi in the center is 0, the other two can be non-trivial but cancel each other. So this is just to show from general theoretical analysis point of view, Euler angles are not a good coordinate system. But which one is a good coordinate system? We have seen it. Axis angle variables are very good. They obey all these conditions. They obey this convention about the identity. Now, apart from saying that for each element there is a well-defined set of parameters and the identity shall be always represented by the origin in the parameter space, we have not put any further restrictions except continuity. So this means that we always have the freedom to change parameters, or freedom to change the coordinates that you use to label group elements. So, and this I will keep mentioning off and on. So what you have to imagine is, the notation has to be, as I said, very carefully controlled. You take a given element A and you say, instead of assigning it the coordinates alpha 1, alpha 2 to alpha r, I will assign some new coordinates, alpha bar 1, alpha bar 2, and so on. So what will be the requirement on such permitted changes of coordinates? Given the values of the old coordinates, all the new ones must have well-defined unambiguous values. Given the new coordinates, the original must also have well-defined unambiguous values. So it means the old and the new coordinates must be clearly obtainable from each other without any problem within the region where they are defined. And moreover, since our convention for the identity will always be respected as a matter of convenience, any changes of coordinates we might make will always have to obey this condition. If the old coordinates happen to be 0, we will make sure the new coordinates, however they may differ away from the identity, at the identity they will remain 0. So this is a freedom which we have and which we will use somewhat later. Now let us come to serious stuff. You take an element little a, element little b. A has coordinates alpha, B has coordinates beta. The group tells you there is a procedure to compose the elements A and B and to produce a third element C. The coordinate distribution tells you if A has coordinates alpha and B has coordinates beta, their product must have some coordinates which we will call gamma. So what does it mean? It means that there is a system of real functions f indexed by j as a superscript. Each of these functions is a real function and each of these f's has two are independent real arguments, r alphas, r betas. And what do? They give the coordinates of the product element AB from the coordinates of A and of B. So the structure of the group, the composition rule or composition law of the group is described in a given coordinate system by a system of numerical real coordinates functions. So I want you to be very careful. The number of functions is little r. The number of arguments, independent arguments in each function is 2 times little r. Now we have made a convention about the identity element. That convention implies immediately certain properties for these functions. Okay. What are those properties? Let me ask you to tell me. I should be able to write down an equation in terms of these f's which contains this rule that we have adopted. What does it say? Huh? Fj of? Little more than that can be said.
Fj of alpha 0 is alpha.
Yeah.
Alpha j.
Yeah.
J of alpha 0 is alpha j.
Yeah. Something more?
J of 0 alpha is
Yeah, exactly. So between the two of you, you have got all the statements I was hoping to get. This is just an expression of our convention, but it is quite important. All right. Now we are going to analyze one by one the properties of a group and see how they are reflected in this kind of numerical description. Now we know, because we have a group, that if we have an element A, of course in that neighborhood it has a unique inverse. We know that, and we know that that inverse can be applied on the left or on the right, and both ways it will give us the identity element. We know this because the group is given. We will just assume our neighborhood is carefully chosen, so that whenever we have to deal with the inverse, we make the assumption the inverse is also there. It also can be assigned coordinates somewhere or the other. So we will imagine, given this point in coordinate space alpha denoting the element A, there is a point somewhere else which denotes the coordinates of the inverse of A, and I will put some values for that. I will say, I'll call the coordinates of inverse of A shall be labeled as alpha prime.
then
Yeah.
say that D groups
Yeah.
in the neighborhood of identity can be assumed up to approximation that it is a subgroup, because
No.
we are assuming that AB is in that neighborhood.
I am assuming that I choose elements A and B such that their product also is in the neighborhood.
Okay, this is not valid for
Yeah,
A.
but see, suppose I start with A. Then if A is an element of the group, so is A squared, A cubed, A to the 4th. I can go up to A to the 10 million. How can you make sure that every power of A will stay within this neighborhood? There is no reason to expect it. Some stage you are likely to go beyond the neighborhood you have chosen. Okay? So it's not a subgroup, it's a subset, but for purposes of analysis, whenever we have to deal with elements and their coordinates and operations with them, we will limit ourselves to choices of group elements so that we always are within this neighborhood. We never say group operations can never take us out of this neighborhood. If we were to say that, it would be a subgroup, but no, we are not saying that. I think it's a nice question you asked, and so I also feel I am explaining things very well today. It's the early part of the day. So very good. So in this language of so these are called the group composition functions. Group composition functions. In the language of the group composition functions, if I gave you the coordinates alpha of an element A, what are the equations I should solve in order to get the coordinates of A inverse? What should I solve? F of? Exactly. So the way you are supposed to discover the coordinates of the inverse is to solve this system of equations. Now we make the assumption, and we don't, actually it's not an assumption, we are guaranteed, if we are given a group to begin with, and if we have a faithful, unique, continuous one-to-one coordinate description in some neighborhood, given alpha, there will be a unique set of alpha primes which will obey this equation, this set of equations. There are n r equations here. J goes from 1 to r. And supposing you take some values for alpha, you solve these equations, so we are guaranteed the solution alpha prime is unique. We are guaranteed that, assuming A inverse is in our neighborhood. Moreover, something else is guaranteed. What is that?
Equal to Fj alpha prime alpha.
Exactly. Why? Because we know we are dealing with a group, and we know that an inverse can be applied on the left or on the right. So the coordinates alpha prime of the inverse of a group element can be obtained from the coordinates of A itself, either by solving this set of equations or by solving this, and we can be sure, we have no doubt, whichever we solve, the answer will be the same. So this is a coordinate based description of how inverses are supposed to be obtained. Yeah?
When you say this, is it necessary that all the sets of unique alpha will also belong to this RR?
I'm sorry, I've not caught your question.
So when we are saying that for every alpha, there exists an alpha prime.
Every alpha meaning every set of numbers alpha 1, alpha 2 up to alpha r,
there exists alpha.
whether provided that alpha is within that region. You cannot go very far away like Bangalore or something. All right, within whatever region we are discussing. Yeah.
So for that, is it necessary that all the alpha dashed of 1, alpha dashed of 2 till alpha dashed of r will also belong to this region?
That we assume. We can't prove such a thing. We will imagine we take an element within our neighborhood which we have coordinatized. Understand? And then we will take A to be such that its inverse, whose existence we have no doubt because we have a group. We will assume A is such an element in the neighborhood such that its inverse is also in the neighborhood. You assume. All right? So all manipulations, arguments are in a region sufficiently close to the identity so that we do not run into any problem. So just to answer your question, if we make that assumption, you give me this point in the coordinate description with the coordinates of the point being alpha 1, alpha 2 up to alpha r. The moment you give me that, this point is uniquely determined. Its coordinates are uniquely determined by this. How? Either you solve those set of equations or you solve this set of equations, and we are guaranteed whichever you solve, the answer will be alpha prime will be the same. Yes, sir. Please say it. Does this answer your question? Okay. Now I said earlier that we always have the freedom to change our system of coordinates. Instead of alpha, we might change to some alpha bar. And I just want to indicate how we must approach such a change of coordinates. Let me rub out some of these things. So I want to just say a little bit about this feature. You have to become comfortable with a certain notation. Imagine making a change of parameterization in which the alphas n and the r independent variables alpha are replaced by r independent functions of themselves, and collectively I denote this change of coordinates by the symbol phi. So we have several functions here. For the first component, phi 1 of alphas. For the second component, phi 2s, and so on. So this is in a compressed way describes a change of all the r variables. It must be such that, so then you go to the element. So this was for the element A, this was for the element B. It had coordinates beta to begin with. We switched our coordinate system. It has coordinates beta bar. Then what is the system of coordinates for the product element? Before we changed the coordinates, we said group composition is given by a system of functions called the group composition functions, f of alpha beta. Then I ask, what will be the new coordinates in this consistent notation gamma bar for the product element C of A and B. What should I write here? What should I say? Phi of f of alpha comma beta. Wonderful. However, if you are switching wholesale to a new coordinate system, everything must be expressed in that coordinate system. Now here, for C we are using new coordinates, for A and B we are using old coordinates. So you must develop this further, and so you see that it becomes necessary to invent a little further symbol to say if alpha bar are obtained from alpha by a set of equations phi, these equations must be uniquely invertible. If I know the old coordinates of A, I give you a rule how to find the new coordinates. If I give you the new ones, I must have unambiguous values for the old coordinates. So it must be possible to invert this change of coordinates and symbolically write it in this way. So phi inverse is not 1 over phi, it is not the inversion of one function, it is a collection of functions, a transformation which has an inverse, and this symbolically represents the old in terms of the new. Then what should I write here? I should write phi. It gets a little bit one more bracket, is it? Correct? And now what is the natural notation for this? In the new coordinates, group composition is described by a system of composition functions f bar. So you must keep this in mind, that if you change the description consistent with our conventions, this is what is going on. So this is equation 7. Actually, things like this we learn when we study general theory of relativity, when you study tensor calculus and possibility of changing the coordinate system in a smooth manner, not limiting yourself to Lorentz transformations but arbitrary changes of coordinates. Such ideas are there also. So if you have already studied that general relativity, this what I am saying now will appear sort of familiar. But we are doing it in the context of a Lie group, that is the only thing. Okay. Now, so for a little while I will not change coordinates. So here are the functions f which describe the group composition law. These are R functions of 2 R variables each. Now by a very interesting argument, we will obtain some sets of functions which are more basic or which are elementary compared to these group composition functions. And what is it that we do? Well, the argument is as follows. Again, I have to draw a little diagram. Where shall I draw the diagram? So the aim is to show you that in a natural way, one can go from the f's to something little more elementary. How do you do this? So first let me draw the diagram. So this is to supplement that figure. Here is the identity element, and it corresponds in our Euclidean parameter description to the vector with components 0. Here is an element A, with the parameters alpha. All right? Okay. Now, imagine taking a point in the parameter space close to the identity. That means it has parameters delta alpha, which are assumed to be small quantities. So, as a group element, this point is an element of G very close to the identity. Now, so I will not give it another name like A. I will not call it delta A. I'll just say an element which in the description in Euclidean space sits very close to the identity. Now I can do two things. I can take the element A and multiply it. So let me just symbolically write this. I take the element A and I multiply it on the left by an element in the group very close to the identity. That idea of being close is indicated by the symbol delta alpha. What will be the coordinates of this element? Let's suppose, since I multiplied it on the left, it brings me to a point here. So this is the element which I obtain starting with A, multiplying on the left by an element close to the identity. What will be the coordinates of this point? What are the values of my parameters at that point? Well, it is just this, right? Because I have multiplied on the left. Now imagine, so this is the region of the space, parameter space, whatever you like. You imagine you were dealing with some function, say real, complex, doesn't matter, some function, let's say real function on the group, a real valued function on the group. So at A, it has the value phi of alpha. This is abuse of notation, but I'll just write it that way. By how much does phi change its value when I make this small shift on the left? This is called a left, infinitesimal left translation. By how much does the function phi change? Well, it is clear that I'm asking for the value of the function at a point close to alpha, but obtained by a small element of the group applying to A on the left. So what will this be? Now, so I want to develop an expression, formula for this. So now I do the following. I say I will develop first a Taylor series expansion for this function. When delta alpha is equal to 0, how much is this? Just alpha. Then I will say I'll keep up to first order terms. Correct? I am making a Taylor series expansion with respect to the variables in the first compartment of the function f. At delta alpha equal to 0, that's a unit element, the value is just alpha j itself. So this I will give a notation like this. Okay? I start with the functions f which depend on two group elements by taking the Jacobian matrix of derivatives with respect to the first variable, first group element, and then setting that element equal to the identity. I get a system of functions eta which depend only on one group element. They depend only on A. Now these are very important functions. So now you can put this together and you will see to first order in these delta alphas, the change in any function capital phi is given like this. So let me write here what I wrote there. The etas are functions of only R variables, that means are functions of one group element, obtained from the group composition functions by imagining that the left hand element in the composition law is coordinates and then set the coordinates to 0. So this I will say, so you can say the change in the value of a function on the group under this small left translation I will write it symbolically like this, where capital X is equal to, what is it equal to? A first order partial differential operator with respect to the parameters defined at each point of the group. So from group composition functions which depend on two group elements, and therefore in a numerical description two are independent real variables, we have produced a set of functions, more functions, R squared functions, but each one of them is a function of a single group element. So these etas are very, very important in the development of the theory. You could have done all this in the other order. You might have said, instead of multiplying A on the left by an infinitesimal element, you multiply it on the right by an infinitesimal element. Then you will go in that direction. And then you will find, so if you want I will write delta left here, that's not in my notes, but this too is obtained by applying a certain first order partial differential operator to the general function phi. The notation used is like this, and let me give all the details. What are these partial differential operators? They look like this, where how do you think the eta roof is obtained? You start always with the group composition law. Now you compute the Jacobian with respect to the right hand side group element. That's the only difference. So now I am losing track of equation numbers and so on. Anyway, this is 9. So to now I rub out this diagram because I have motivated these two things. You find that, so let me now decorate them. from the group composition functions by differentiating with respect to the left argument and then putting it equal to 0, or by differentiating with respect to the right argument and then putting it equal to 0, that is setting it equal to identity, you get one set of functions or this other set of functions. Each of these leads naturally to the definition of a family of first order partial differential operators, capital X going with eta, capital X hat going with eta hat. Okay, and these are obviously more elementary than the group composition functions because they are arguments, single group elements. Now I ask the following question. Take this element, so this is a matrix. It is an R by R real matrix. J is the row index, K is the column index. Suppose I ask, what is the value of this eta matrix when its argument is the identity group element? Huh? Beg your pardon? Delta? Sorry, I can't hear. Delta? JK. Exactly. How did you see this? It's true. Where do we put alpha equal to 0? Wherever it is. Here. No, beta has already been put equal to 0. Yeah, tell me the argument. You're correct. This will have become beta k because of the convention about a unit element. So, at the identity, we know in advance that these functions eta and eta roof, which should be thought of as matrices of functions, they both reduce to the unit matrix. At the identity, here eta is a unit matrix, eta roof is a unit matrix. By continuity, we will therefore assume that in some neighborhood of the identity, they remain non-singular. So we will just assume that from the beginning we have chosen a neighborhood carefully, small enough if you wish, throughout which eta and eta roof have inverses, unique inverses. So we will therefore imagine that this has an inverse, and the notation, standard notation is like this. Psi is the inverse matrix for the etas, and for eta roof, inverse matrix is psi roof. So I add so you might think I have this looks like elementary particle physics, more and more elementary particles, more and more elementary functions. I am replacing the group composition functions which depended on two group elements by several matrix functions of single group elements. 4 matrix functions, all of them at the identity are the unit matrix, and in some region around the identity, eta is the inverse of psi as a matrix, eta roof is the inverse of psi roof. These are the relationships. Okay, so this was the argument leading to the etas. So you can see that some sense the etas are the ones you arrive at first by this kind of picture of how a function varies when you shake the argument a little bit, and arriving at their inverses is a next step, because you say at the identity everything is invertible, so you assume you are in a region around the identity where the etas are non-singular. Yeah. Yeah, please.
See, you started off with a neighborhood.
Yeah.
I'm sort of trying to emphasize one.
Ah.
When Sandeep asked a question,
Yeah, whether it's a subgroup.
then you took a neighborhood where the product is also lives.
Yeah.
Then when this young man, I don't know his name, when he asked a question about invert, then
Yeah.
you take a
Yeah.
neighborhood where that is
Yeah.
also true.
Yeah.
Now you are taking a neighborhood where
Yeah.
the
Yeah.
prefix is invertible.
Yeah.
The intersection of all these
Yeah.
neighborhoods
Yeah.
is not real, and that's
Yeah.
will suffice.
Yeah. That's correct. So take the small enough, don't say smallest, there is no such thing as a smallest neighborhood. Take a neighborhood which is chosen conservatively so that all these assumptions and operations are meaningful. That is correct. So I'm glad you made this point. So, as I told you, I learned all this stuff from Professor Valentine Bargmann. So yesterday night, I could not sleep. I was reminding myself, it was for my whole career, it has been my great good fortune that 1 year I was there and I listened to his lectures and took very careful notes. Whenever I missed 1 or 2 classes, I borrowed other students' notebooks and made up a complete set of notes. And that has stood me in good stead up to now. So I hope 50, 40 years from now, some of you will say, we were there in math science when Mukunda came from Bangalore and gave some lectures, and we have found it useful. That is the most important part, that I hope you will find this stuff useful. If you are exposed to it once, even if you do not understand everything now in this 2-3 month period, if your notes are there, you can always come back to them, refresh, understand things better as time goes on. Huh? This book? Beg your pardon? Pontry again. Yeah. Yeah, that's also true. Yeah. But it was Bargmann's lectures which gave me the confidence to try and understand this subject. One thing I want to make clear, it is not that the entire content of this course is based on what I learned from Bargmann. No, that was a foundation. And after that I learned many other things which we will see in later sections. But it was very important that I had this opportunity to learn it from him. If I had not, many things that I have been able to do research-wise since then, I just would not have been able to do. Those ideas would not have been part of me, the machinery would have been unfamiliar. It is just a fact. Second thing I wanted to say is that unfortunately I never shook hands with him. If I had, I would have been, one handshake away from Einstein. Isn't it? 1 or 2, how is the counting? How does one count? Because I assume that Bargmann must have shaken hands with Einstein. He was his assistant for many years, but I never shook his hand. Yeah. And that reminds me of another nice joke. Some of you have heard it. There's a very good friend of mine. He's a professor of physics in Syracuse University, Professor Joseph Schechter. He was a student of Okubo, and he and I were class fellows at Rochester. And in some conversation, one day I told him, you know, in India we have a saying that you take any 2 people, they can connect, person A can find a connection to person B through at most 5 mutual friendships. I said, we have this saying in India. Then he thought about it for a moment and then he said, I can believe you can do it with 10 friendships, but with 5 I am not sure. So I said, why do you say that? He says, because in the USA we have a saying, any person can be connected to the president by 5 steps. So go up to Bush and go down. He has a wonderful sense of humor, and this is something I heard close to 50 years ago. I never forget his answer to what I said. Now Bargmann taught one notation for these things, and I'll just mention it. I suppose it is there in some of those old textbooks. For these matrices, he used to write these symbols. I believe these are the capital letters in Greek alphabet for xi and eta. I suppose so. So sometimes we may use this, but it is simpler when we want to deal with the etas as making up a matrix. We just use eta without superscript and subscript. That is point number one. Point number two, and this I am not very sure about it. We have taken these functions describing the group composition law, and what we so this is off the record, not to be quoted, on condition of anonymity. These are definitely functions which are continuous functions of their arguments. Why? Because we have a Lie group, which is a topological group. Group operations like composition are continuous operations. We have a statement that a Lie group is a topological group in which, in some neighborhood of the identity, coordinates can be introduced such that that neighborhood, the word is homeomorphic to Euclidean space, which means continuity is preserved. So putting all this together, what our definitions tell us is that these group composition functions are continuous functions of alpha and beta, but nobody told us that they can be differentiated. Now, we as physicists may say, look, why should they not be differentiated? But strictly speaking, as far as I understand and recall, the definition of a Lie group as a topological group in which coordinates can be introduced continuously, by itself, I believe, does not guarantee that these f's can be differentiated. And my recollection is Bargman said that this was a problem in one of that Hilbert's list of what, 23 problems? What was it? 13, 20, 17, 23. Huh? I believe this was one of the problems that show that from the definition of the Lie group, the functions f can be differentiated. I can imagine, I can appreciate, you should also appreciate, it's a highly non-trivial problem. A function can be continuous. Well, actually it's very difficult for us to imagine a function which is continuous but not differentiable. You know that such functions exist? Do you know? How many of you are aware of the fact that one can have a function of a real variable which is continuous at every point but cannot be differentiated anywhere? How many of you know it? Don't feel ashamed. I also didn't know for a long time. Yeah, all the rest of you know it, huh? You didn't know. Okay, this is true, and the person who analyzed these questions for the first time and constructed such functions was a famous German mathematician, Weierstrass. And I'll even give you a reference to a book, again a very beautifully written book, where this construction is described. I don't expect you to fully understand the construction. All I want you to be aware is, if a function is continuous, by no means is it differentiable. By no means, strictly speaking. If a function is differentiable once, by no means is it differentiable two times. By no means can you assume there is a Taylor series with infinitely many derivatives. But, so these are very delicate points, but we will behave just as we assume our neighborhood is so nice that it will have products, inverses and everything. We'll also assume the functions can be differentiated. And my impression, again I may be wrong, from Bargman's lectures I recall his saying that this Hilbert problem, to prove that the functions describing group composition are in fact differentiable, this proof I believe was given by two mathematicians by name Montgomery and Zippin. I don't know when it was done, I have not seen their paper, this is just my recollection. If any of you is curious, you might try to find out, is this true? What I am saying, is this correct or not? And this Weierstrass construction of a function which is continuous everywhere but cannot be differentiated anywhere, a very beautiful book. It's written such a nice, easy style that even we can, get a understanding of it. It's a classic book. The title, I think, is Functional Analysis by Rees and Naj. I even now remember the initials, the names. See, all these come back after so many years. And Naj, this is a name which V. Srinivasan would be happy to see, Imre Naj. So, just if you have time sometime, you go to the library, flip through the initial pages of this great book, Functional Analysis by Rees and Naj, and you will see this Weierstrass construction described there. I bought this book at that time, in those days, 1965 or something. It's a substantial book, 2-3 times the size of Pontryagin group theory book, but this is also something I will never give away. Okay. Would be differentiable. True, but the definition of a Lie group does not assume diffeomorphism. Homeomorphism is all it assumes. Okay, so I don't know this subject very well. I mean, so many beautiful mathematicians said, you ask them. I am afraid to go and ask them. They will say, you are almost 70 and you don't know this, they will say to me. But you please go, you ask them, you know this is an interesting problem. Go and talk to Professor Ramanan or somebody. He's giving a course on Lie groups, I think. And ask him, is this true? What is the argument? What is the status of it? Huh? My understanding is, again, I may be completely wrong, Hilbert's idea was, I think, that the condition that you must have a group is so strong that it will allow you to prove differentiability. That's my impression, but I may be wrong.
Your recollection is that Hilbert, when he proposed his problem, he thought that diffeomorphism follows from group property and continuity.
That is homeomorphism. That's my guess. I am not.
And your belief is that these two guys, Montgomery and
Zippin,
have proved it affirmative.
Yeah, they solved one of the Hilbert problems, and I suppose it was sometime in the 1940s or some such thing. I'm not very. In fact, I'm giving you 1 day break tomorrow. I'll come back on Monday. If any one of you has the time to just check, talk to somebody, find out, come and tell all of us what is all that I have said now. Is it really so? If it is not, what is the real truth? Okay, just I'd like you to do a little investigation, but please don't tell Professor Ramanan who told you all these things. Okay, because I must protect my reputation in his eyes.
What is the definition of diffeomorphism?
Huh?
Definition of diffeomorphism?
Diffeomorphism is a one-to-one onto invertible mapping which is continuous and differentiable in both directions. So diffeomorphism is between differential geometric manifolds. So it assumes you can differentiate any number of times. All right. A mapping from one manifold to another of the same dimension, invertible, and in both directions differentiable any number of times. Homeomorphism is a map from one topological space to another with an inverse continuous in both directions, bicontinuous. Homeomorphism does not say you can differentiate. That is important. And my understanding is these gentlemen, Hilbert made this a problem and they solved it. But just try to find out. There's another very completely unrelated but interesting thing. You may have all heard of a famous theorem called the Kam theorem. It is in what subject? Nonlinear mechanics. Huh? So this was a theorem, I think, which was first conjectured by Kolmogorov, and it was proved by Arnold and independently by Moser, as far as I know. one of them, see, this is a problem in classical mechanics, and some functions appear, and my impression is that the person who found the proof first assumed that some functions which appear in the proof can be differentiated 233 times or something like this. The other person simplified it. No, it's enough to differentiate it 17 times. I don't know if this is a joke somebody made on me, but it is really true that the first time this theorem was proved, a very strong assumption was made. I don't know why this odd number, something more than 200 times something had to be differentiated. The other man showed that much is not needed. Okay. So, what I want to now say, so now starts the real analysis. I stress here, group composition is given by functions of two elements, naturally. These are the things which actually define our group structure, how to multiply two elements, how to find the inverse of an element, and so on. From the analysis point of view, differential equation study of this whole thing, the more elementary objects are these systems of matrices. A matrix eta, its inverse psi. A matrix eta roof, its inverse psi roof. Much of the study can be done in the language of eta and psi, or parallelly in the language of eta roof and psi roof. The results are completely the same at the end. So we now have to very carefully study a host of properties of these three collections of functions, the f's, the etas, and the xi's. And there are four things that we have to study. I will write them down. Each one is a fairly extended study. We have to study how associativity is expressed in this language. Second, the concept of one parameter subgroups. Third, integrability conditions. And Lie algebras. And four, reconstruction of the Lie group from its Lie algebra. So this is a real program. There are four things to be done, and each one is something which requires quite a lot of attention. But I want to list everything, so it will all not be done in one day or in 1 week. This whole thing may take us 2 weeks or so. Incidentally, today is the 11th lecture that I am giving, right? So just past the 25% mark. So I hope that you have an idea where we are heading. What is it called these days? Roadmap, is it? In the political language. This is what we are going to try and do one by one, slowly. So just one moment. Let me cross out what I have done. Okay. So the number of pages I will be able to cover from my notes each day will be somewhat less than it has been in the last few lectures, because I think for most of you this is new and I don't want to rush over it too much. So we begin with the analysis of associativity. So I have given you enough time to write down these 4 things. I want to start with a clean board. So item 1, associativity. This is one of the key elements of group structure. We will see it can be expressed as a system of non-linear partial differential equations. We will now study what associativity means. We will show by assuming the functions we are dealing with can be differentiated as often as we desire. We will show that one can express the associativity property of group multiplication through a system of partial differential equations. So now suppose you take 3 elements in the group. Of course it is in our neighborhood, the product is also in the neighborhood. I don't have to, it's by assumption. Associativity says the product of these 3 can be computed in 2 ways and the answers will be the same. So if a group is given to you, you know that this property is there. And what does this mean in the language of the group composition functions? When there is no need for a subscript or superscript, I will just omit it. The F's, the group composition functions, are very special. You are guaranteed that you are dealing with a group, and F is an expression of its composition law, and therefore it must obey this system of equations. Now these are not differential equations, these are functional equations. Now I do the following. Now let me bring an index here. So J goes over 1 to R. I say the following. Differentiate both sides with respect to gamma k, then set gamma is equal to 0. That means you differentiate with respect to both sides with respect to the coordinates of the element C, and after differentiation take C to be the unit element, identity element. Alright? So now tell me what will be the left hand side when I do this. Maybe I should first write it and then, so here is what I am doing. What will I do for the right? See, in the left hand side, the variables with respect to which I want to differentiate are there out in the open. So the left hand side is very easy to write. But on the right hand side, the gammas are hidden inside the f of gamma and alpha. So I can't immediately differentiate. I have to use a chain rule. So if I use the chain rule, I want you to appreciate that what I get is this. I want you to appreciate that the right hand side, when differentiated with respect to gamma and then gamma is set equal to 0, gives me what I have written, where L is summed over. That is the chain rule. Because what is happening is that I must differentiate this quantity with respect to the components of gamma. So So what I do is I differentiate with respect to the components of this whole argument, any general LH component, and then the LH component of that with respect to gamma. And then I have to put gamma equal to 0. Putting gamma equal to 0 would in any case collapse this to alpha. That accounts for this first term. And then the chain rule tells me the second term. Alright. So now, what is the left hand side? Do you recognize it as something we have just defined 10-15 minutes? Sorry, so this is wonderful. What shall you dictate what I should write? Eta, superscript, subscript, K, argument. Oh, wonderful. Equals. I can't do anything here. And what is this? Eta, L, K, alpha. Beautiful. All right. So Bargman would be really happy that through me you have come this far. What I can now do is the following. This is a matrix product on the right. This is an invertible matrix. Its inverse is psi. So I can rewrite this exposing these partial derivatives. And first let me write the left hand side and you tell me what I should put on the right hand side. What is this equal to? Eta j. Yeah, wonderful. Psi. Where is L and where is K? No. KL. Alpha. All right. Clear? So, imagine that the F's were, no, let me put it this way. If a Lie group was given to you, you chose a coordinate system the way we have described with our conventions. You know that group composition in that Lie group is given by some functions f alpha beta, and you know, because you know associativity is valid, those F's are going to be obeying the system of nonlinear partial differential equations with respect to the alphas. In these equations, betas are like spectators. But there is a way to bring in the betas. We can say that if we think of alphas as running variables, betas as parameters, we would make the statement at running variable equal to 0, we have initial conditions or boundary values. So the betas in this equation appear as boundary values of functions of alpha obeying a system of nonlinear partial differential equations. Why nonlinear? Why is it nonlinear in general? The F's, the unknowns, think of them as unknowns. They are arguments of the etas. And who knows what the etas are? The etas themselves are complicated functions of their arguments. Now, you might like to know, what do the functions eta and the functions psi look like for the rotation group, SO3 or for SU2? It is nice to know what they look like. They involve cotangent functions and things of that kind. And if you look at our book, Sudarshan and my book on classical dynamics, in the appropriate chapter, the chapter on the rotation group, the etas and xi's are given there for the rotation group in axis angle variables. So you will get a feeling for what these functions are and how the etas and the xi's are mutually inverse matrices and so on. So tonight, I have borrowed that book from the library. I suppose there's only one copy. No? Anyway, it is there. I will leave it with Simon. Just out of curiosity, if you want to know in a practical case, what do these functions look? Practical, non-trivial case, like the rotation group, the expressions are explicitly given. Maybe I should have written them down, but I don't. All right. So, in this notation which I said I will use sometime, I can write it in this form. Eta will stand for the matrix of eta jk's, psi will stand for the matrix of psi jk's, and here is the equation, system of partial differential equations. So, the situation is like this. If a Lie group was given to you, and if you chose a coordinate system, and if you computed the group composition functions, they, we know in advance, obey this associativity property. From this, assuming we can differentiate again, we are able to show that the group composition functions are solutions of this system of nonlinear, in general nonlinear partial differential equations with respect to the alphas as the running variables, and the betas enter through saying when the alphas are 0, each f is equal to a corresponding component of beta. So, this is the sense in which associativity leads to a system of partial differential equations. So, is this completely clear? I have gone over it very, very slowly.
So this right K and L. K and L stand for row and column.
Beg your last one.
No, this right K L like
Here,
yeah.
this is a row, this is a column. Yeah.
Here it should be right transpose.
No. This is this
Because the inverse,
column and row summed over.
inverse of eta L K.
Yeah.
We went from this equation to that equation.
Yeah.
So eta L K, inverse of eta L K is.
You don't talk of the inverse of an eta lk. You talk of an inverse of the matrix of etas. Don't think that psi is the inverse of an individual matrix element eta. No, no. The whole matrix inverse.
But that equation will multiply both sides on
Yeah.
right by psi k some other parameter and then
Yeah,
sum
yeah,
over K.
yeah. Correct. So let us say you multiply both sides by this. Both sides.
sum
And then you
over
will
K.
get this. Of course, sum over k because it's repeated. Then you will get this. Is that clear? Okay. All right. So now we explore the meaning of these equations in the following way. I will stop in a few minutes. I will rub out all of these things which led to that equation, system of partial differential equations. And I will describe the situation as follows. We ask the following question. If a group is given, a Lie group is given, and you choose some coordinates in some way, the functions f alpha beta are known to you. From them, the functions eta are known to you, xi's are known to you. So, we will say, given G and choice of alphas, f, eta, psi are all known. Correct? Also you know that because associativity is guaranteed, it implies those equations, what's it, number 15, are obeyed. The system of partial differential equations 15, all of those equations are obeyed and the boundary values are also properly realized. Okay, now we ask the question, is the converse true? What is the sense in which you ask this question? if somebody gives you a matrix of functions eta and the inverse matrix of functions psi, so both are non-singular, if eta and psi are given, and remember these are the more elementary objects because they depend only on one group element, can we solve 15 to get f alpha beta? If so, can we use it to define a group composition law? Will associativity be valid? Will inverses exist with properties we desire? This is a question we ask. I hope you understand. If the G was already given and you chose your coordinates, that system is satisfied. No question, no doubt about it. One wants to know, can one go backwards? If the simpler quantities, eta and psi, as functions of R component real vectors, if etas and psis are given and we know that mutually inverse as matrices, can we start with those differential equations? Can we solve those equations, get the f alpha beta, and then say, now I am defining my group, I will say the f gives me the group composition law. If I do that, will it be a group? Will the associative law be satisfied? Will each element in the group I am trying to construct, will it have a unique inverse? Will the inverse act on the left as well as on the right? All this must be satisfied if we want to have a group. Now it's a very interesting situation. There are two situations. I told you once, there was a film 50 years ago called Me and the Colonel. I don't know who among you has seen it. Danny Kaye and Kurt Jurgens. Very beautiful film. I don't know if there is a film club in Chennai with old classic films. Anyway, in that, again and again, Danny Kaye says, in life there are always two possibilities. So now in this there are two possibilities. So I hope you have written down this question which you are asking, and I'll tell you these two possibilities. And I want to make this discussion a little more lively. Are there any girl students? Oh yeah, one, only one. Okay. I'll tell you what are the two possibilities in answer to this question. I will write it out from my notes. Someone else knows some Lie group G and has the functions f alpha beta in her hands. She gives you only the functions eta and of course the inverse. This is scenario 1. Then we can make the statement, then the PDEs 15 can be solved uniquely by you, I am stressing, by you, to get f alpha beta. you can then use this solution and set up the group. So this is situation 1, that she has the group in her hand, but she doesn't tell you what the group is. She does all the computations. She knows what the F alpha beta are. From them she calculates the matrix eta and the matrix xi. Doesn't tell you what group it is, but only gives you etas. And you do the work of finding the xi, the inverse matrix. Then if you are assured there is a group, I'm not telling you what the group is, I'm only giving you the etas, you can reconstruct the group. You have the full confidence those equations are consistent, they can be solved, there will be a unique solution for F alpha beta, and if that F solution is used to define group composition, it will obey the associativity property, it will have, every element will have a unique inverse, all properties will be satisfied. You can construct a group out of the information she gives you. The only thing you do not know is the global properties of the group. And that is understandable because this is an analysis of group structure near the identity. So subject to that, not ambiguity, it's freedom, we can say that this is the situation. This is case 1. I will now describe case 2 and then I will stop. So I want to emphasize, somebody has a group already in his or her hands, and so the F's are really there, they exist. It's just not known to you. You are given only the etas and xi's. You can find the F's by solving those equations. Those equations are solvable. That is the important thing. Second alternative, like Danny K says, she does not know if a group exists, but just gives you some matrix of functions eta with the inverses alpha. I mean, this much, at least decency, it must be a non-singular matrix. This much she will guarantee. She gives you some matrix of functions eta. Just one moment. With the appropriate boundary value. Unit matrix when alphas are 0, that is given. She guarantees that the choice of matrix eta is such it has an inverse. Then your question is, so she doesn't know if the group exists, she just picks up a matrix of functions, non-singular, equal to the unit matrix at the origin and says, now come, find a group, construct a group. So you ask the question, can you try and solve the partial differential equations 15? Can you find functions f alpha, beta which obey those equations? Can you use them to define a composition law? Will it be associative? Will inverses exist? So many questions we are asking. And therefore, will you end up with a Lie group starting from those differential equations? What do you think is the answer? The person who gives you the etas and xi's doesn't know if there is a group or not. If she knew there was a group, that is taken care of by this alternative. And then you know that the solution exists. It is just that she knew it and you did not, but you can get it from those equations and everything will be pakka. But if she also doesn't know whether there is a group, just try some set of functions eta, make them make sure they are a non-singular matrix, etc. And she says, here I am giving you these etas, build a group. What do you think is the answer? The answer is no. In general, the answer is no. For arbitrary choices of the matrix eta, provided it is non-singular, 15 are inconsistent. As mathematical equations, as partial differential equations, they are inconsistent, they have no solution. In order for these equations, so an arbitrary choice of etas will not lead to any group. The functions eta which arise from groups are very, very special. And only if by chance the choice she makes happens to be one of those special etas, only then the whole machinery will work. So you have to ask the question, when do you know that these equations are consistent? What are the conditions for consistency? If they are consistent, then it means it can be solved. Will there then be a group composition law? Will there be a group? The answer is, the condition of these equations possessing a solution is called integrability conditions. Unless these conditions are obeyed, it is not possible to solve those equations 15. They don't have any solution. Now, the idea of integrability condition is extremely elementary. You know it already in electrostatics. What's an example of an integrability condition in electrostatics? If I have given you an electric field E and I want it to be the gradient of a potential, can I write this for arbitrary E field? No. It must have curl 0. That's an integrability condition. This is a very trivial first order partial differential equation. It can be solved only if E has certain properties. Those are the integrability conditions. Here also, the equations 15 can be solved only if etas are very special functions. Those special functions are those which obey certain conditions called integrability. And now the answer is, first we'll find those conditions, later on we'll find them. If those integrability conditions are satisfied, then we can go all the way. We can say, then one can solve this equation, one can find the f's, and it will be true that the associative law is valid. The only thing that is missing in this reconstruction is global properties. So what we can say is that if one knows that there is a group in the background, in the picture somewhere, one knows associativity property is fully captured by a system of partial differential equations. And what we have to study now are two things. And I will stop after this comment. One is slightly easier than the other. The first thing we will have to do is the following. Case A. We are given a situation where we know that solution exists and solution is unique. We must explicitly prove that if the solution of this equation is used to define a composition law, that composition law will have the associativity property. This we will prove, start proving on Monday. Later we will see how do you ensure in the first place that a solution exists. What are these integrability conditions? That study will lead us to the concept of the Lie algebra. Okay, so I stop at this point.